All right, it's been a while, but anyway, here I am, and today I want to talk about two topics. First, I know I've talked about mobile phone lens designs before and why there are a lot of wiggly surfaces, but I want to show you one simple example for why, in some cases, you got those very wiggly surfaces. All right, that's the first topic. The second topic is going to be why, when you are using an even asphere surface shape for your lens design, why I think that if you put a variable for your conic constant, you can actually put variables on your fourth order, sixth order, eighth order, and all high orders all at the same time. And despite the fact that in university, you might be told not to do that. You might be told if you put variable on your conic, you should not put variable on your fourth order term. You should put it only on your sixth order and high orders. There's good reason for that as well. But here I'm going to show you, or later on in topic two, I'm going to show you why you can actually go ahead and put variables on all those orders, except for the second order. Okay? All right, so the first topic. So, um, why is it that you see many wiggly surfaces? Okay, well, in many cases, wiggly surfaces are there because you have a very compact system and you want to correct so many aberrations. And in most cases, you are actually doing that, it's correcting a lot of stuff. But what can also happen is that if you have too wiggly of one surface, while it's correcting aberrations, it can also create problems for other surfaces as well. And those other surfaces have to be wiggly to correct the problems from the first wiggly surface. So to show you a very simple example of that right here, I have two glass slabs, right? Here you can see two glass slabs and parallel rays from infinity going from left to right. And they go through unperturbed because you're just going through flat windows. But what happens if I do this to one window? This surface here now has this weird shape. It's causing perturbations to the rays, and the rays are no longer parallel, right? How do we fix that? Well, we can fix it with the second surface. We just make the second surface right here do very similar thing. There you go. All right, one wiggly surface causing problems. The second wiggly surface fixing it to some degree. You don't really you can't really make it exactly the same. It has to be perturbed a little bit more so that the rays are exactly parallel. But they're somewhat the same, and I knew that because if in the limit that the airspace is zero, like this, then what you have is just a crack in the glass slab with zero airspace. So you can do any shape you want. You can make it like this, for example, and everything's fine, right? But if you put it farther apart, things start to vary. I purposely gave it a small perturbation so that I can pull the glass surfaces far apart, and you won't see much ray variation or ray errors, ray aberration. So anyway, here's an example, right? Again, one surface causing problems and the second surface being wiggly to correct it, like in a mobile phone lens. So that can happen. Right? I'm not saying that it is always happening, but it can happen. Okay, so now that's topic number one. Topic number two is about even aspheres. So let's do that. Let's go to this. Okay. Okay, so what do I have here? This is the typical even asphere formula. You've got the sag for the surface. You've got this, the curvature with a conic constant, and then you've got all these aspheric terms, right? So usually you're told that if you use a conic constant and you put a variable on here, then you should not vary this coefficient. You should vary this coefficient and higher order coefficients. All right, and you're also told not to vary the second order coefficient, and it's for good reason. Why? Because this whole term here can actually be expanded just like these terms here in a Taylor series, like that. Okay, so if you expand it to say three orders, second order, fourth order, sixth order, then you've got these three terms here, and you can see the similarity between these three terms and these three terms, which are from over here, right? You've got some coefficient times r squared. Here you got the coefficient times r squared. So if you're varying the A2 coefficient here, you are screwing up with this coefficient here, which is 1/2 times c, and c is 1 over your radius of curvature. So you are kind of messing around with your radius of curvature if you're messing around with this coefficient. So we don't want to do that. All right. Uh, and then you're also told that if you're varying your conic constant, you're messing around with your fourth order coefficient. So if you're putting a variable on your fourth order coefficient, they're kind of fighting one another. But by the same reasoning, if you are putting variables for your next coefficient, your sixth order coefficient, you're also fighting this coefficient here, which is all this stuff here times r to the sixth, and so on and so forth. So by this reasoning, it's kind of unreasonable to say that you should not put a variable for your fourth order coefficient when you're varying your conic constant, because you're doing the same thing for your sixth order and so on and so forth, right? So you can do it for everything. But if you have just third order spherical aberration, for example, which is fourth order in wavefront error, then it is true that you shouldn't muck around with other orders. Just muck around with your fourth order term. Or in some cases, if you know you want to solve all orders of spherical aberration only, then put the variable on the conic constant, right? And forget about varying all these other terms here, because your conic constant can fix that spherical aberration. Especially, for example, if you've got an axial ray beam and you want to, you know that you need a hyperbolic surface to create your proper phase and make everything go to zero for aberration, for spherical aberration to all orders, then you know that by aberration theory, your conic constant has to be equal to negative n squared, where n is the refractive index of your material for that wavelength. Okay, so that's one condition. But in most cases, as I said, if you're varying your conic constant, then you can vary these as well. Think of these as perturbations to these terms here. If your conic is not doing a good job, then these terms can perturb these corresponding terms in ways that could be beneficial for you. And speaking of that, by the way, even when the conic constant is zero, when these are zero, look what happens to the formula when k is zero. You still have these coefficients, right? When k is zero, you got 1/8 times c cubed, 1/16 times c to the fifth power, right? You still have these coefficients. So if k is zero, then you still have, when you're not varying your conic constant and you're varying your fourth order term and sixth order term and so on and so forth, then these are also fighting with these coefficients here, right? Fighting. In most cases, they're not really fighting. They are perturbations to these terms here to solve for the wavefront errors caused by aberrations, right? But by the same token, if these guys can perturb these guys, then these guys can perturb these guys as well, and you're all set. Okay, so that is what I want to say tonight, and I hope you've learned something useful here. And that's it. Bye bye.